All right, I want to demonstrate some of these projects, starting with C503. So, first I ought to mention the new projects. There's a group I'm not going to demonstrate tonight, but I realized we're using Python more and more, and I didn't put in the introductory Python stuff. So at the bottom, I added the introductory Python stuff, which is almost all cryptography anyway. So this is all here for extra credit if you want it. Setting up Python and cracking password hashes, the Caesar cipher, XOR, AES, and Argon 2 hashes. Those are new projects, although they're from another course, from another workshop I did in Python, but I realized they ought to be here because we are using Python more and more. And so feel free to do that stuff if you like. But the first thing I want to do is the math projects tonight. So let me go back to my list, which is here. Okay, 503. 503 is here, finding large primes. And this is something you have to do. So we got Fermat's little theorem that says a to the p minus 1 is always 1 mod p. So that is an interesting, any number raised to the p minus 1 would be 1 if p is prime. And so if you try various a's, if you have a number and you think it might be prime, you can take that number. If you have a p that you suspect of being prime, you can take a random value of a and see if this is true. And if it's false, you know that it's not prime. 1 mod p, defined one mod anything is always 1. The mod p applies to both sides of the equation. So that's what this means. That's why there's this space here. So you take a to the p minus 1 mod p, and then you get 1. Yes, that's an important thing to know. If it was just on this side of the equation, it wouldn't make any sense at all. Yeah, good. I'm glad you brought that up. So anyway, this is a condition which will tell you if something is not prime. If this is not true, then it's definitely not prime. And therefore, if you try it for several values of a, and it always turns out to be true, then you gain increasing confidence that p is in fact really prime, although you haven't really proven it. It turns out that just trying it 5 times is pretty good. So let's try this. This is a simple program, and it's fermat.py, and I think I've already got it here. All right, let's try ls. Yeah, so if I cat fermat, all right, what this is going to do is input a potential prime from the user, and then it's going to take a random integer, and then it will see if the power of a to the p minus 1 mod p is 1. And if it's true, it says pass, and otherwise it prints fail. So if I run this, Python 3, Fermat, and I give it, say, 5, it passes. If I give it, say, 100, it fails every time because that's not prime. If I give it, I think 101 is prime, though. Nope, yeah, 101 is prime. So that's what happened. You see, it is pretty good. You might imagine that it might sometimes fail. Fermat. Fermat, I'm pronouncing Fermat wrong. I could Fermat. Oh, could be. These French people. I don't know anything about French. Anyway, so boy, I think I've heard scientists calling him Fermat all my life. Anyway, so there you see that's the game. This is a way to detect a potential prime. All right. So you can do large numbers. Here's a number that's 1,024 bits long. And Python just does it very nicely. So that's 1,024 bits long. And you can see pass, 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 pass. Python calculates everything to, it doesn't matter how big an integer is, it uses it, as long as you're careful to keep everything an integer and not let it switch to floating point mathematics. French can have their luncheon as long as we can enjoy the pastries. Yeah. They're, anyway. So that's the game. And so now, now you see we can tell when we find a prime by doing this test. But then you might ask, how many times would you have to guess to find that prime? And that is a problem that's also been solved centuries ago. It's the density of primes, and it's 1 over the natural logarithm of n. And so that's easy to calculate in Python too. And this is one I put in. So that is density. So let me just cat density up there. So all this does is input. It tells you I'm going to take n is 10 to the x, and it inputs x. So I can try really large numbers. And then it says n equals 10 to the x and just prints out 1 over the log of that. So if I run Python 3 density, if I do 10 to the 2, 100, then 21% of the numbers up to there are prime. But if I do 10 to the 10, it's only 4% of those numbers that are prime. And if I do 10 to the 100, 100-digit numbers, 0.4% of them are prime. And if I do 300-digit numbers, which is what 1024-bit keys are, 300 digits, then about 1 of those in 1,000 are prime. And if I do a 10 to the 1,000, which is like a 3,000-bit key, then 0.04% of them are prime, 4 in 10,000. So it's not impossible to find them, but you might have to do 10,000 guesses to find one. And that's why it starts taking a long time to do the generation of keys. It's having to guess thousands of times to find P and Q. But it doesn't have to guess, 10 to the 20 times or some insane number like that. It's not as bad as you might think. It really won't take that long for a computer to find a prime number. The density isn't that small. So this also tells you when you're doing, the reason I added this is it gives you a clue how many reps it's going to take to solve the puzzles below. This tells you how long it will take to find a prime number, because here's a game. I'm going to start you with this number, which is not that long at all, maybe about 30 digits, and I want to find the next prime after this. So just start with that number and count up until you find a prime number. And here, start with 10 to the 100, the 100-digit number, and find the first set of companion primes above that. Companion primes are 2 prime numbers that are only separated by 2, like 3 and 5 are both prime, so they're companion primes. 5 and 7 are both prime. 7 and 9 are not, because 9 is not prime. 11 and 13 are companion primes. So that's right. So 2 primes that are as close together as they can be, which is separated by 2. And the companion primes exist all the way up to. And so you have to find the first companion prime after 10 to the 100. So there's a couple of challenges to do. And you now know how to find a prime, and you even know how likely it is to find a prime, so you can have a clue how many guesses it's going to take. And it won't take forever to answer either of these. All right, so I'm going to stop this one, the recording.